Joe, can you see from there? You okay?
Yeah.
All right, good. Okay, so find plot test 7.3. And you can keep your dry erase board handy because you might need it for sketching out shapes. Or you can sketch on your paper, whichever you prefer. Bless you. All right, well, first we know what ions tend to do, right? They react to form noble gas configurations. All atoms do. They all want to get to the most stable configuration, the lowest energy, right? So what do metals tend to do? They give electrons away, or we lose electrons, subtract electrons, so that they form cations. Remember, cations are the positive ones. It even has a plus sign in the middle of its name, so you remember. Cations are positive. What do nonmetals do?
Share electrons.
They're going to accept or gain electrons in covalent bonds. Share. Works better here than gain. Oh, didn't mean to do that. Because this is covalent. Good reading, Brian. Okay, then in our next place, that's where we're going to say, what? Sorry, guys. That they can gain electrons to form anions. Just an example of answer the question they asked, right? You're not the one you want to do that. You know, I have to show you all the ways to mess up so you don't have to do them all yourself. In ionic compounds, when we're looking at an ionic compound, we are mainly talking about a solid crystal. Ionic compounds tend to have really high melting points and distinct melting points. Covalent compounds melt over a range of temperatures, but ionic compounds have a melting point that's measurable. The ions then align themselves to maximize attractions between opposite charges and minimize the repulsion between ions with the same charge. So again, we have Coulomb's law popping its head in mind, right? Good old physics. Gotta love it. And we're always working to get to noble gas configuration because atoms know where they are on the periodic table. They don't know if they're left or right or up or down. Why did they do this? What makes it more stable? Right, but why is that stable?
Because there's no more places for it to bond.
Just like teenagers, they want to be at their lowest possible energy, right? Mama, let me sit on the couch. I'm not getting up to do chores. I don't know, it's not just teenagers. I'd rather sit on the couch than do chores too, quite frankly. Go have a nap. That sounds glorious. I don't know if any of you feel sleep deprived this week. Yeah, I'm feeling your pain. You betcha. Okay, so let's talk about if we're going down a group, that means we're adding more energy levels, right? Adding more rings. Yeah, if you write it, I will sign it. What does the ion size tend to do as you go down a group and you add another layer of electrons? Right. So now if I take my atom and I remove the electron, what's that going to do to this size? Okay. And I want to be clear about why this happens. So let's turn calcium into calcium 2 ions. Okay. So we had this kind of Bohr diagram, 2, 8, and 8 and 2, right? If we give the last 2 electrons away, then look what happens to your shielding effects. I go from being in energy level 4, now I'm in energy level 3. because I gave these ones away. So that in its own creates less shielding. I did have this much shielding, now I only have this much, right? But I also have a greater difference in charge. 20 are holding in only 18 electrons now instead of 20 electrons. So think about it like babysitting. First you were in charge of 20 kids, and then Mama came and picked up 2 of them. Now you only have 18. It's easier to keep track of them all, right? Okay, what would anions do? They would get larger because we're adding more electrons, and so now you have to babysit more kids. It's harder to keep track of it, right? And the shielding would increase because then you get up to a higher energy level. So across the row, they get smaller and then suddenly larger because you go from cations into anions, right? So the first half, which ones are those? The cations. And the second half, anions. Sorry, was that too fast? No. Okay. So these periodic trends keep coming back. They're not going away. Across the period, the nuclear charge is going to increase, and that makes the cation smaller. Increasing nuclear charge is referring to the number of protons. So phosphorus has 15 protons, and sulfur has 16 protons. So we're increasing the nuclear charge. The energy level changes between the anions and the cations. So the anions are larger because the cations drop down to a lower energy level. So they're going to be smaller. Here's an example of that row too. So our smallest cation was carbon with the 4+. What if I made the anion carbon with the 4-? Bigger than nitride, do you think? Yeah, probably so. Okay, let's answer a question. Let's put these in order for their increase in atomic radius. So find germanium, silicon, selenium, and chlorine on the periodic table. Let's put them in order. And this is increasing atomic radius. Which ones are the smallest ones? Right, the ones with fewer energy levels. So when we're in row 3, we have fewer rings, right? Okay. And now between these two, who's going to win the tug of war? Because silicon has more protons? Oh. So let's answer that question again. Who's going to win the tug of war? Chlorine has more protons. If you have 17 people pulling against 14, this guy wins the tug of war. That makes it smaller because it pulls its electrons in tighter. Right? So these are atoms, not ions. Okay? So chlorine is our smallest, and then silicon. So it looks like this is a good choice, right? Now let's check the other two options. In row 5, who's going to win the tug of war? Right? Okay, so 4 is still looking good. So your first decision is about the energy level. Your next decision is about nuclear charge. And make sure you answer the question I asked. Some of you got the reverse order on your Unit 6 test. Okay, what does iso mean? So isoelectronic means? the same number of electrons. And an isosceles triangle has?
Same.
Oh, okay, see, iso means the same. All right, so we have these ions. They're considered isoelectronic. How could that be? They're all so different. How could they all have the same number of electrons?
Because of ion. Plus they have
Okay, so some of them gave away electrons, and
some
some.
gain. Plus they could all be the same.
Right. They all look like this guy, right? So that would be 1s2, 2s2, and then 2p6. So fluorine had to gain 1 to have 2p6. Sodium had to lose 1 because it would have normally been 3s1, right? So they all ended up looking like the configuration of neon. They all have 10 electrons. They all have the same configuration. And so what about their sizes? Oops, yeah, positive. Ions have more protons. So they're smaller than your anions. So here's the ranking. Is that how you would have predicted it? Okay, I think there's room for you to sketch and label. Now, all of this is bringing us to energy. Bond energy is determined by Coulomb's law, right? So we have our constant, proportion constant, times the charges, divided by the square of the radius. What does the square of the radius have to do with the ionic size? Right, so the bigger the ion, the more space it's going to take up when we put it together with something else, right? The smaller the ion is, the closer we can get them together. And so that's going to affect the energy in the bond. You ready? Got your picture? So let's form ionic compounds. This type of energy is called the lattice energy. It's the energy associated with making a solid ionic compound where it's not a true molecule, but rather it's a proportion of the ratio of atoms in that structure. So if we take some metal, combine it with some nonmetal in its gaseous form, then we make a solid ionic compound. Remember, energy is a state function? So we may have to go in a series of steps, but the overall energy change is going to be the same. So for us to break bonds and turn metals into gases, sounds like that's going to take a lot of energy. But the lattice energy is what we gain back in the end. When that compound forms, we're going to have some payoff. And what if the payoff isn't worth it? Then it won't happen. Unless we make it happen, because we're chemists, right? Oh, controlling the universe. Now we don't remember what I was going to say about this. Oh, state function. Aha. I already said that. Getting ahead of myself. Energy is a state function. So we can get to the overall energy change in a roundabout way, and it does take some work. It's called the Born-Haber cycle for calculating lattice energy. So the first thing we have to do is sublime the sodium solid into sodium gas, and that's going to cost some energy. The next step is to turn the gas atoms into ions. This is called the first ionization energy for sodium, right? Then we have to break a bond between the two fluorines because fluorine's diatomic, right? So we have to break that bond. That takes some energy. Then we have to gain an electron for fluorine. And that one looks like it's exothermic, yeah? Why would that step be exothermic? It's losing energy? Well, fluorine's going to get to a lower energy state when we add an electron to it, right? So if you started at a higher energy state and you end up at a lower energy state, that's exothermic. Okay. Now for the lattice energy, we're going to add all of those steps together like you did with Hess's law. Start canceling out things that show up on both sides. So what can you get rid of? Let me see what we had. Oh yeah, calm down. Here we go. So F gas, Na gas, electrons, okay. So we formed ions, right? And they stick together because what? Because opposites attract, right? So add all your energies together, and do you get the same number as I do? Get your calculator out and add the energies together. Don't be lazy. So here's our lattice energy, where K is a constant that depends on the structure of the crystal. And Q are charges. R is our internuclear distance, and that's going to depend on what kinds of ions there are. So the lattice energy will be greater if we have more highly charged ions, because then your Q's would get bigger. That also means they would be forming stronger bonds, right, if it takes more energy to break it. And we would anticipate then a higher melting point, a higher boiling point, and all of the other physical properties that go along with having a higher lattice energy. So here's an instance for the Born-Haber cycle for lithium fluoride instead of, we did sodium fluoride before. Here's lithium fluoride. So let's track each step. We start out here with solid lithium metal and half of a fluorine atom. So first we have to sublime the solid. That takes energy. And then we have to take its electron away. And what was our next step? Breaking the bond and getting the fluorine atom by itself. Then adding an electron to it. And then we form the lithium fluoride. And so this is probably the piece we were missing. Yeah, so that 900 number is probably this number, and the overall charge is the sum of everything. But I'll have to look that up and see. I will, I promise. Oh yeah, that reminds me. The review for your final exam I've been trying to print since Wednesday. The copiers are broken again. And so I have the bubble sheets for your final review. And I have printed on my list exactly what kinds of calculation problems you can expect to see, so you'll know what to study, and some examples of multiple choice, and the bubble sheets so that you could check your answers. But I don't have the ability to copy them for you right now. So I'll try and track you down. If I can't, I will see you tomorrow at Mesa Ridge. And if I don't see you there, you can download it from my website.
So, yeah, my game
Yes.
is at Canyon City, so...
Oh,
yeah,
it's not the home game.
Yeah, they switched it.
Oh, that stinks. Okay, well, you have to manage your own life. I don't get to tell you what to do. By the way, if you miss the bus tomorrow, get yourself down to Mesa Ridge, because the bus here is leaving at 7:30, but we won't actually start the sessions until 8:30, so you'll have time to get there in time for donuts.
They didn't
Yeah.
have donuts there
Or
when
whatever.
we were there.
No snacks?
Not in the breakfast.
Oh, okay.
They didn't have donuts. They
I'll
had
have
Oats
donuts.
for glow.
There's like the Nutri-Grain granola bars.
Oh, okay. Something healthier than a donut.
Well, they had like gourmet lunches.
Brilliant. I'll bring you an orange chip. Or grapefruit. Do you have a preference?
I can't eat either of those either. But do they get insulted if I bring my own food?
Absolutely not.
Okay.
No.
This is like we're just here.
And of course, you all know Mrs. Wallace has been helping to organize all of that. She's like our main person getting it all together. So we're really glad for her. Yes, she'll be there. Okay, the bigger lattice energy pays for the extra ionization energy, and it pays for unfavorable electron affinities that may exist. And so, let's decide who's going to have the higher lattice energy of this group. How do we decide? Which one is more ionic, or which one has more highly charged particles? So what's the charge of cesium?
1 plus
Okay, chlorine. All right, zinc.
Oh god, +2.
Those two. Sulfide.
-2.
Calcium.
+2.
Fluoride.
-1.
Okay, sodium.
+1.
Chlorine.
-1.
All right, which is our more highly charged pair? And of course, diamond is carbon with carbon. Not even ionic at all.
So zinc.
Right, this would have a higher lattice energy. That doesn't make the strongest bond, because that would be this guy. But we'll get to covalent solid networks in the January when we come back from the break. Let's do some more delta H. So covalent bonds are created by forces that cause a group of atoms to behave as a unit. These are not ions, and so when we make covalent bonds, we're not transferring electrons, we're sharing electrons, right? We move electrons around so that they can have partners. Why would they do this? We get to the lowest energy. Okay, wait, sit down, because you're not done yet. Here's what we're going to do for bond energy. You're going to take the bonds broken minus the bonds that are formed. So you may have to sketch out where the bonds are. Every bond has a certain amount of energy. So if we're going to burn methane, then you have to sketch where the bonds are. How many bonds do we have to break here? 4. And they're all 4 carbon-hydrogen bonds. So we would look up this bond energy and multiply it by 4. Then we have oxygen. Oxygen has this kind of a bond. So we have to look up the energy contained inside the O double bond. And we multiply it by 1. But then, guess what? You're going to have to balance this equation. Right? Is this one balanced? So you need 2 here. How many oxygens?
4
Okay. So then I have to take this energy and multiply it by 2. We're not quite done. Because there's going to be 2 in the balanced equation. Alright? So we take the bonds broken in the reactants and subtract from that the bonds that we form in the reactants. So we ran out of time to finish our notes. We'll finish them on Monday but I would not anticipate this to be highly featured on your final. Definitely expect molecular geometry to be on your board. Okay?